Hey there, space fans! Ever imagine a volcano erupting not with fiery lava but with ice-cold slush? Welcome to the fascinating world of cryovolcanoes, icy cousins of the fiery mountains we have on Earth. Instead of molten rock, these cosmic volcanoes spew out volatiles, stuff like water, ammonia, or methane. These materials, normally liquids or gases on Earth, freeze solid in the ultra-low temperatures of the outer solar system. Think of it like this. Imagine taking your iced coffee out on a cold day. It stays liquid, right? Now imagine that same coffee in the deep freeze of space. It wouldn't just freeze, it would become hard as rock. That's what happens with the volatiles erupting from cryovolcanoes. Join me as we explore these icy wonders, their eruption secrets, and how they might hold the key to finding life beyond Earth. So, what exactly are these cryovolcanoes? They're basically volcanoes that erupt with icy materials instead of molten rock. They look and act like volcanoes, just with a much cooler twist. Instead of fiery lava flows, picture geysers shooting jets of water ice into space. Imagine mountains sculpted from frozen ammonia or methane instead of hardened magma. That's the basic idea behind cryovolcanoes. These icy volcanoes form on planets and moons far from the sun, where temperatures plummet to hundreds of degrees below freezing. In these frigid environments, even familiar substances like water behave in extraordinary ways. Cryovolcanoes are a testament to the incredible diversity of our universe, showing us that volcanic activity isn't limited to molten rock and scorching heat. They remind us that nature always finds a way to surprise us, even in the coldest corners of space. Now, let's talk eruptions. Unlike their earthly counterparts, cryovolcanoes don't erupt with fire and fury. Instead, they offer a spectacle of icy plumes and frosty flows. The magma in these volcanoes is actually a slushy mix of ice and other frozen volatiles. This icy slurry is less dense than the surrounding ice, causing it to rise to the surface and erupt. The eruptions themselves can be quite dramatic. Imagine towering geysers of water ice shooting kilometers high, or vast plains of frozen ammonia spreading across the surface. But remember, everything happens in slow motion in these frigid environments. Eruptions might last for years, even decades, slowly reshaping the surface of these icy worlds. So where can we find these icy wonders? Well, head towards the outer solar system, where temperatures plummet and ice reigns supreme. One prime location, Jupiter's moon Europa. This icy world is thought to harbor a vast, salty ocean beneath its icy shell, potentially heated by tidal forces from Jupiter. And guess what? We've spotted evidence of cryovolcanic activity on Europa, hinting at the possibility of an active, watery world beneath the ice. Then there's Saturn's moon Enceladus. This little moon is a veritable cryovolcanic powerhouse. It boasts massive geysers that erupt from its south polar region, spewing water ice and organic molecules into space. These plumes are thought to originate from a subsurface ocean, making Enceladus another promising target in the search for life beyond Earth. But it's not just moons. Pluto, once thought to be a cold, dead world, surprised us with evidence of cryovolcanic activity. This discovery suggests that even in the farthest reaches of our solar system, these icy volcanoes are shaping the landscapes of distant worlds. Section 5: Cryovolcanoes. Fountains of life? Now here's where things get really exciting. Remember those subsurface oceans we talked about? Well, scientists believe that cryovolcanoes could be the key to unlocking their secrets and potentially finding evidence of extraterrestrial life. Think about it. These icy plumes erupting from cryovolcanoes offer us a glimpse into the hidden depths of these icy worlds. By studying the composition of these plumes, we can learn about the chemistry of the subsurface oceans and maybe even detect signs of life. Imagine finding traces of organic molecules or even microbial life in the icy spray of a cryovolcano. It would be a game changer, revolutionizing our understanding of life in the universe. So, while cryovolcanoes might seem like strange and distant phenomena, they could hold the key to answering one of humanity's biggest questions. Are we alone in the universe? Section 6: Studying ice volcanoes from space. Now you might be wondering, how do we even study these icy volcanoes located millions of miles away? Well, we turn to our trusty robotic explorers spacecraft. Spacecraft like NASA's Galileo, Cassini, and New Horizons have given us our first close-up views of cryovolcanic activity. These missions have flown by icy moons, snapped stunning images of erupting plumes, and even sampled the composition of these icy geysers. For example, the Cassini spacecraft orbiting Saturn spent over a decade studying Enceladus's plumes. It flew through the plumes, analyzed their composition, and even detected organic molecules, hinting at the possibility of a habitable environment beneath the moon's icy shell. These missions have provided invaluable data, but there's still so much more to learn. Future missions, equipped with even more advanced instruments, will be crucial to unlocking the secrets of cryovolcanoes and their potential to harbor life. Section 7. Earthly Fire versus Cosmic Ice. So, how do these icy volcanoes stack up against their fiery earthly counterparts? Well, they're both expressions of volcanic activity but with some key differences. Firstly, the driving force Earth's volcanoes are powered by internal heat, while cryovolcanoes are driven by internal heat and tidal forces from their host planets. Secondly, the materials molten rock for Earth, icy volatiles for cryovolcanoes. This difference in composition leads to vastly different eruption styles and landforms. Finally, the environment Earth's volcanoes erupt into a relatively warm, oxygen-rich atmosphere. Cryovolcanoes, on the other hand, erupt into the frigid vacuum of space where temperatures plummet to hundreds of degrees below freezing. Section 8. The birth of an ice volcano. How do these icy behemoths even form? Well, it all starts with internal heat and tidal forces. Imagine a moon orbiting a giant planet. The gravitational pull of the planet creates tidal forces, stretching and squeezing the moon's interior. This tidal flexing generates heat, melting the icy materials inside. This melted ice, mixed with other volatiles, becomes less dense than the surrounding ice, causing it to rise towards the surface. As it rises, it can create cracks and fissures in the icy shell, eventually erupting onto the surface as a cryovolcano. The exact processes involved in cryovolcanic formation are still being studied, but tidal heating and the unique properties of ice play crucial roles in shaping these icy landscapes. Section 9. The Impact of Cryovolcanoes. Cryovolcanoes aren't just cool geological features, they have a profound impact on the environments of the icy worlds they inhabit. For starters, they replenish the atmospheres of these worlds, releasing volatiles that would otherwise be trapped beneath the surface. These volatiles can contribute to the formation of thin atmospheres and even create temporary clouds or hazes. Cryovolcanic eruptions can also resurface these icy worlds, creating new landforms and erasing older ones. This constant resurfacing can make these moons appear surprisingly young, despite their ancient origins. But perhaps the most intriguing impact of cryovolcanoes is their potential to transport materials from the subsurface ocean to the surface. This transport mechanism could have implications for the development of life, potentially bringing nutrients and energy sources to the surface where they could be more readily available. Section 10. The future of cryovolcanic exploration. The study of cryovolcanoes is still in its infancy, but the future is incredibly exciting. Future missions are already on the drawing board, poised to revolutionize our understanding of these icy wonders. One such mission is NASA's Europa Clipper, planned for launch in the coming years. This mission will make multiple close flybys of Europa, studying its icy shell, subsurface ocean, and yes, its cryovolcanoes. The Clipper will be equipped with a suite of advanced instruments including ice-penetrating radar to map the thickness and structure of Europa's icy shell and potentially even detect plumes erupting from its interior. Another exciting mission on the horizon is the European Space Agency's JUICE mission, or Jupiter Icy Moons Explorer. This mission will study 3 of Jupiter's largest moons, Ganymede, Callisto, and Europa, all of which are thought to harbor subsurface oceans. These missions, and others like them, will provide invaluable data, helping us to unravel the mysteries of cryovolcanoes and their role in shaping the icy worlds of our solar system. Who knows what incredible discoveries await us as we continue to explore these frigid frontiers.